Hello everybody, it's Amberton. Today we're going to be going over Cramer's rule and how this can solve. Today we're going to be doing two variable system equations and three variable system equations. How Cramer's rule can solve this. Cramer's rules involves matrices, so please watch a video on matrices and how to find determinants. I may go over the determinants today maybe, but this is going to be involving matrices, and it can solve two variable system equations, three variable system equations. This is Algebra 2, MAO Lesson 1. So MAO is like a it's I think it's national, but like it's mainly like there's like a huge base in Florida. Basically, it's based on the subject that you're currently learning in your math class, and basically it's a competition based on that. So Cramer's rule is going to be our first lesson, and these are going to be advanced. So first of all, for a two variable system equation, it shouldn't be that hard to do it without Cramer's rule, but you can still involve Cramer's rule in this. So we're going to be trying it with Cramer's rule. So let's pretend we have this: 3x plus 5y is equal to 19. X plus y is equal to 5. So obviously you can do a lot of elimination here, but let's try it with Cramer's rule. So basically, Cramer's rule, we set x equal to something and y set equal to something. And it's basically a matrix, a 2 by 2 matrix because there's two variables, 2 by 2 matrix in the numerator and a 2 by 2 matrix in the denominator. Same here. So in the general Cramer's rule, the denominator is always called the coefficient matrix. Now, based on this name, you should be able to get this matrix right, but it's just basically taking all these coefficients and putting it here. So you're going to go 3 here, 5 here, 1 here, and 1 because 1x plus 1y. And also both x and y have the same coefficient matrix. So quickly, if you know determinants, how do you solve this? Well, in a 2 by 2 matrix, if you had a 2 by 2 matrix over here with variables a, b, c, and d, the determinant will be AD minus BC. So it's going to be AD minus BC. So what will it be here? It's going to be 3 times 1 minus 5 times 1. That's equal to negative 2. So the denominator is negative 2. Now the top one will be different for both because of course x and y are not going to be the same. Now it can be the same. It's very rare though. It's very rare that x and y will actually the matrices will be the same, but the solutions can be the same with different matrices. So basically, we have to involve this 19 and 5 here because you could do a 3x plus 5y to anything. So we haven't involved that in the denominator. So in the x side, pretend we're going to write what we had in the denominator first: 3511, 3511. So how do we incorporate the 19 and 5 into here? Well, for the x value, you basically, this left side, or the coefficients of the x values in both of these equations, get replaced by 19 and 5 respectively. Same here. 3 and 1 will get replaced. No, so now 3 and 1 here. 3 and 1 stays here, actually. This one, because it's y, you change this to 19 and 5. Because you're going to have different values. So we can do the same AD minus BC method. So 19 minus times 1 minus 5 times 5, that's equal to negative 6. This one, 3 times 5 minus 19 times 1, that's equal to negative 4. So you can clearly see that we got 3 and 2 answers. So I'm going to subtract. So remember, x is equal to 3, y is equal to 2 using the Cramer's rule. Now, are we actually right? Yes, you can probably plug it in. And to be honest, after you find the x value, you probably could just plug in and find the y value. But I just wanted to show you both. Now, plugging in, yes, it's going to be right. But let's see if we do it by elimination. Let's multiply this by this last equation by 3. We're going to minus this, so it's going to get 2y is equal to 4. Y is equal to 2. And now, yes, you can plug in probably, and you'll see the 3 and 2 work. So that's how we can do it with 2 by 2 systems. Now, on to 3 by 3 systems. 3 by 3 you could also do, it's a little bit with more like subtracting, so sometimes it does get very confusing. But let's see. So, we're going to have equation x plus y plus z is equal to 5. So remember, this is 3 variables now. 3x plus 2y plus z is equal to 11. And 2x plus 4y plus 3z is equal to 15. Now I'm going to say this has integer. So this one's a little bit, of course, tougher, because determinants of 3 by 3 are a little bit tougher. And there's 2 ways you can do it, but I'll tell you which one is probably the easier way. Well, it's basically the same method, except now you have a z. So you set x equals y equals, and then z equals. And this time, we're going to make the box a little bit bigger due to the fact that we have a 3 by 3 matrix this time in both the numerator and the denominator of each variable. Now, the denominator is still going to be the coefficient matrix. And this, of course, I outlined in the last one. Sorry, this one's a little bit slanted. So, you can use a coefficient matrix. So, we're going to have 1, 1, 1. Let me just write all of here. 1, 1, 1. 1, 1, 1. 3, 2, 1. 2, 1. 2, 1. 3, 2, 1. 2, 4, 3. 2, 4, 3. Now, let's do the same method we did last time. Let's write the same thing. Right here, 2, 4, 3. 2, 4, 3. Let's write the same thing in the top, because we're going to be replacing one of the columns. Okay, so we wrote the same thing in the top. But, so, what will we do? Well, for the x, it's almost the same method. We're going to replace this left column with our solutions here that we haven't used yet, which is for solutions for each linear equation. So, not linear equation, but each equation. So it's 5, 11, and 15. It's not a linear equation, right? That would be a plane. Okay. Oh, so I accidentally wrote that. But this is supposed to say the same. This middle column is going to change to 5, 11, 15. Finally, for this last z, we're going to change that to 5, 11, 15. So, let's find the equations for each one. Well, how do we use it for a diagonal method? So I'm not going to use any ABC because this one's a little bit harder. I'm going to write here. So let's use the coefficient because we're going to have to find that. So there's two methods. You can use submatrices, which involves a formula which you memorize. And to be honest, at least for me, I always forget that one. I use diagonal method. What is diagonal method? Well, let's place these first two columns to the right of this matrix we have. Now we have it. Now diagonal method, you can guess it. Basically, we add all of the upper left to the lower right diagonals. So that's going to be like that. I didn't write that exactly that right. So what is that? That's 1 times, and remember we're timesing 1 times 2 minus 3, 1 times 2 times 3, plus 1 times 1 times 2, plus 1 times 3 times 4. We're going to minus that in parentheses, so it's going to all negate in the end. And remember, we don't have any, I didn't put any negative coefficients, so all will become negative. So that's going to be 2 times 2 times 1. I think this is 4 times 1 times 1. Yeah. 4 times 1 times 1. And 3 times 3 plus 1. 3 times 1. That is going to be equal to the determinant. Now, submatrices I would just involve in a video, but I think personally this one's better. So, we do 6 plus 2 plus 12 minus, remember it's all going to negate, minus 4 minus 4 minus 9. Let's solve this. 3. So this is equal to 3. Unless I get anything wrong, this should be equal to 3. Yeah. Now, I'm going to erase this so I have enough space for the next one. But you should get it, and please watch that again if you don't get it. But this is basically the diagonal method. Now, I may go these next ones quick, because this is a little bit time consuming, I would say. So, if I would actually recommend this if you're, because subtracting equations sometimes does get a little bit confusing, I agree. Like, I don't really like it. Cramer's rule, of course, the diagonal thing, it's a little bit time consuming, but it may be more safe. So, let's times this. So, I'm going to do this quickly. So, that's going to be, so let me write my columns here. And let's quickly do it. So I have a little bit bigger values due to the fact that my solutions for each one are a little bit bigger. But let's try. So it's going to be 30, 15, plus 44, minus 30, minus 20. Is that 20? Minus 33. So 45, 89, 59, 39, and 6. So you get 6 as the determinant for this one. So what was this? X is equal to 6 over 3, which is equal to 2. So you got 1. Now you could, of course, make it a 2, what's it called? Now you have to solve, let's solve for y. And then z you could, of course, substitute in the end. But let's just do all of them for here. So it's going to be 33 plus 10 plus 45. So what is that? That's going to equal to 88 minus 22 minus 15 minus 75. Sorry, read that wrong. That's 45. I thought for a second, how's that 75? 66, 51, 6. This one's also, so y is equal to 6 over 3, which is also equal to 2. So we got x and y equal to 2. Now, obviously, you can find out the z is equal to 1 by just substituting it out, but let's try it to see if we're actually right. So that's equal to, what is that equal to? That's equal to 112.